Okay, so this is a video on that has to do with how do we use linear algebra with respect to ordinary linear differential equations. Okay, so this isn't going to be a deep dive on how to solve linear differential equations, but it's how is linear algebra tangential to the subject as an application. So we got to first look at what an ordinary differential linear equation or linear differential equation is. Okay, so essentially I have some set of functions, g0, g1 to gn minus 1, and one other function called f. And these things have to be mapping from some domain into the real numbers, okay? And then what we're going to do is we're going to say I have an equation where I have the nth derivative of y plus g sub n minus 1 to the n minus 1th derivative of y plus out to g sub 1. Oh, this should be of x here. Of x, g sub 1 of x times y prime plus g sub 0 of x times y is equal to f of x. And this is a linear differential equation. Okay, so it's a bunch of functions times a bunch of derivatives of y is equal to f of x. Okay, so if f of x is 0, so when f of x is the 0 function, we call this homogeneous. And when f of x is not explicitly 0, we call it non-homogeneous. Okay, so we're getting some terminology there. Okay, so if given the g's and f, y makes the equation true, then y solves the system. So the solution, or not the system, the diffie-q, the differential equation. So the solution to the differential equation is an ordinary equation, y, that makes this true given all of the g functions and the f. Okay, so let's bring this to an example so we can understand what we're talking about here. Okay, so y double prime minus y, y is equal to 0 is a second order linear differential equation. It's about as simple as they get. And if you look, y equals e to the x solves this. Namely, because y prime is e to the x, y double prime is e to the x, which means e to the x minus e to the x is 0. It's a solution. Likewise, y equals e to the negative x solves this. Because y prime is negative e to the negative x, y double prime is e to the negative x, and e to the negative x minus e to the negative x is 0. So both of these are solutions to this second order linear homogeneous, because that's 0, differential equation. So pretty simple, straightforward there. All right, so this leads and begs a question. Like, can we say something about these solutions? And we can. Okay, so this gives us a theorem, which I'm going to leave without proving. But if I have some what do you call it? Nth order, let's just do dots there. Some nth order linear differential equation that is homogeneous, right? So I want this to equal 0. Then I can draw a conclusion. That if I have a set of solutions, A1, A2, out to AN, right? I should make those Y's probably. They're not sequences, they're functions, right? So let's make that Y1, Y2, out to YN is a set of solutions. And this set is linearly independent. Then these basically would serve as a basis for the general solution. So then y equals some constant 1 times y1 plus some constant 2 times y2 out to some constant n times yn is a solution to the system. And all of the solutions can be written this way, where C1, C2, out to Cn are elements of the real. So we call this the general solution to the differential equation. So ultimately, in our last example there, y equals C1 e to the x plus C2 e to the negative x is the general solution to the system, or not the system, the differential equation y double prime minus y equals 0. So in order to say this, the set has to be linearly independent and the function, or the differential equation, has to be homogeneous. Now, that being said, we're not getting into how do I find the particular solutions. We do have a way, though, of determining whether or not this system, or set rather, this set of solutions is in fact linearly independent. And this is what we're going to call the Wronskian. Okay, so we're going to get a thing called the Wronskian. All right, Wronskian is actually a determinant. So the Wronskian eats a set of functions, y1, y2, out to yn. And it returns the determinant of, well, the first row is just the set of functions, y1, y2, out to yn. The second row is the first derivatives. And then we keep doing that until we get the y1 n minus first derivative, y2 n minus first derivative, out to yn n minus first derivative. And we take that determinant. So this determinant of the matrix of the various derivatives is what we call the Wronskian. Okay, so let's give an example of that. Okay, so let's say I have the set of functions x, x squared, x cubed, and I want to take the Wronskian of this set. So the first row is just going to be x, x squared, x cubed. The second row is the derivative of these. And the third row is the second derivative of each of them. Now, we had to take the determinant of this. So this is a determinant, right? So this is going to give me a scalar back. And if you remember, an easy way to do this with like 3 by 3 matrices is to repeat the 2 rows and go down. So this would be 12x cubed. Right, so this is going to be 0. And this one gives me plus 3x cubed, right? 3x cubed. And then we subtract going up, so that's minus 0 minus 6x cubed, right? And then what do we get here? Plus 6x cubed, is that right? Let's see. Yeah, that's, or sorry, minus again. that's a minus 6x cubed because it's going up, right? So minus 6x cubed. All right, so this cancels with that, and that leaves me with my Wronskian as something goofy here. 2. This is 2. X cubed times 1 times 2 should be 2x cubed. There we go. So this is the Wronskian, is 2x cubed. All right. So, like, what goes on here? If this is not materially identical to 0, okay, so this is another theorem here. If the Wronskian is not identical to 0, which here it's not, you can put some values for x in there that are not 0, then the functions that are being tested are linearly independent. Okay, so x squared, and x cubed are obviously linearly independent. When you take the Wronskian and you don't get something that's materially equal to 0, we know that these are linearly independent. This is an application of the derivative to be able to talk about a set of functions. Let's look at another example of this. Okay, so let's say we want to find the general solution to y, the third derivative of y, plus the first derivative of y is equal to 0. So this is linear, it's homogeneous, straight up, and it's third order, right? So we should be able to find 3 solutions. One thing that's really clear is that if I let y equal to 1, there we go, let y equal to 1, that solves it because the first derivative of 1 is 0, the third derivative of 1 is 0, 0 plus 0 is 0. Okay, let y equal the cosine of x. So this is going to give me negative sine of x. This one's going to become sine of x, so that will wipe out. And if we let y equal sine of x, this one is cosine of x, that's negative cosine of x, and that'll wipe out. So these 3 are in fact solutions to particular solutions to this. So we can use them to write the general solution if I can establish that they are linearly independent. I can do that by calculating the Wronskian. So I have 1 times cosine x times sine x. This goes to 0, negative sine x, cosine x, which goes to 0, negative cosine x, negative sine x, right? So we repeat these, 1, 0, 0, cosine x, negative sine x, cosine x, and then we do the downs, right? So that's going to give me sine squared x. This down gives me 0. This down gives me 0. And then we do the ups, right? So that's going to give me 0. This one gives me cosine squared x. This up also gives me 0. Right? That's a negative there. So this is going to be negative. Negative is a positive, right? So this is giving me sine squared x plus cosine squared x, which is equal to 1, which is definitively not 0, which means that these 3 equations are linearly independent. If they are linearly independent, and I have all 3 of them, because this is third order, I now have the general solution, which is C1 plus C2 cosine x plus C3 sine x would be a general solution to this third order linear differential, homogeneous differential equation. All right, so this is how you use the Wronskian to solve, or not solve, but at least create a general solution for a third order or a nth order homogeneous linear differential equation from the particular solutions, from a sufficient number of particular solutions. So there you go. It's another application of linear algebra where we're leveraging this time the derivative or the determinant. All right, there we go.